Hi, good evening. Can you all hear me? Am I audible to you all?
Good evening.
Yes, ma'am.
Okay, good evening. So, is there any doubt or anything from the previous classes, what we saw so far, all the subjects? Is there anything? Anybody? Okay, if not, we will go to reaction kinetics today. And welcome, Nitya. I am seeing your name here. Nitya,
Yes,
you are here. Yes.
Yes, ma'am.
Okay, but almost 80% of the subject is over. Now you are joining. I'm not really sure how you are going to cope it up. Maybe
Yeah.
you can continue the next batch also. I mean, they would have planned next batch in the mid of April again,
Okay.
and you can rejoin in that also. And because today were two more classes. Today we are going to see reaction kinetics and economic analysis. The
Okay.
next class we are going to see that's going to be the last class. Only thermodynamics subject is left over. So next
Okay.
class is thermodynamics. That will be over. So this batch is going to be over. So
Okay.
whatever the topic we saw, that you can continue from the next batch actually. Okay.
Okay,
So
ma'am.
did you put any applications, exam application or anything submitted or not yet anything? What is the status?
Yeah, I'm submitted.
Submitted. Okay. So when have you tried any exam first time or second time, or is it going to be
First time.
the first time? Okay. What is the waiting time? No, they will give roughly idea. So once your application is submitted, have you submitted your certificate or verification all done?
I uploaded, but not yet submitted directly.
Then
So
that will
this,
take some. Yeah.
yeah, this
Understand.
mid of the April, they said.
They will call you. You have to submit your certificates. Then they will take like 1 week. Then they will call you to collect back the certificate. Then
Okay.
from that date, it will take at least 1 month, I guess, right? Or
I don't have idea, ma'am.
yeah, this is what previously, but now I'm not really sure what previously I was talking about. Just like 2-3 months before, once application verification is done, certification verification done, once they hand over the certificate.
Okay.
So from the number, your application number, they will allocate it, including all the engineers, right? They all the electrical, everything. So then
Okay.
it will take like 1 month or something. Only the second or third attempt they will immediately call. The first attempt they will take like 1 month after the certification given back to you.
Okay. Then I have a time.
Time, yes. So I hope you got all the slides and everything from office.
Yeah, I got.
Yeah, madam. Which documents required for the application?
That you check with the office because they have all the attestation, PC. They will have a complete list. They will send it to you.
Okay, clear. Okay, police clearance and all they required, right?
All required, yes. So I think you check with the Green International Office. They will guide you what are the documents to be prepared, what to do, and what.
Okay.
You speak to Mr. Usman or Ranjit?
Usman.
So you can speak to Usman. He will guide you. No problem.
Okay, I will talk with him.
Okay. Any more? Any more questions? Yeah. Yeah, Nitya, you are asking something.
No, I'm okay.
Okay,
Let's
right.
start.
Right. Okay, today we are going to see reaction kinetics. So as I told you, reaction kinetics, roughly you can expect 3 questions and some theoretical, some calculation also sometime. 1 question theoretical, 2 questions maybe in the calculation. Generally what I hear 3 questions, let's take it as average 3 or maximum 5. That way you can take it from reaction kinetics. So here we are talking about the reaction rate constant, right? This is what we are going to see here. That is reaction rate, which is change in the concentration of a reactant or a product with that time. That is in the per second, mole per second generally. That's what moles of delta B divided by delta T. Here the small t represent the time actually. Since reactant go with the time, if it is a reactant, you have a minus, change in moles of reactant. Here it is change in mole in a product. This is for your, no, you have a stoichiometry, A, B, B like this. So you have a change in concentration of A into delta T. All the reactant will have a negative. This all I'm just giving some refresh, some basic thing about the reaction kinetics. Reaction rate or expressions relates the rate of reaction to the concentration of reactant. Each concentration is expressed with an order. Right? That's an order. The rate constant converts the concentration expression into the correct unit of rate, that is mole per second. So, but that also depends upon the unit actually depends upon the order of reaction. Right? So this is a rate is nothing but K is your rate constant, A to the mole of A to the power of N, mole of A to the power of N. So remember M and N are not the stoichiometric coefficient. It is determined from experience in different concentration. They arrive for particular reaction. What is the value of M and what is the value of N? For first order process, if you see, whenever the concentration of reactant falls off exponentially from this way, that's A gives B, that's a first order reaction. So that means change in concentration of A divided by T, that gives your K into A. That's at some particular time, the concentration, that's called here. Okay. So A equal to A naught into e power minus KT. Okay. K is your rate constant, T is the time, A naught is your at time equal to 0. That's the initial concentration. So that when you substitute in this one, you can get a concentration of A at particular time. And if you know the concentration of initial concentration at after 5 minutes or 10 seconds or so whatever, we can calculate first rate constant for first order reaction. Or this is a first order reaction. Please remember A equal to A naught into e power minus KT and ln A equal to ln A naught minus KT. Here it is not log, it is ln. For all reaction kinetics, it's not log, it's a ln. Similar for second order process, rate equal to Ka square. Okay, and if you substitute everything, we'll get 1 by A, which is equal to KT plus 1 by A naught. The same way we relate 1 by A equal to 1 by A naught plus KT. This is for second order. Whatever I'm giving in the bold letter font. So these are the important. For first order reaction, you remember this formula. A equal to A naught into e power minus KT, which is nothing but ln A naught minus KT. Same way for second order also. 1 by A equal to KT plus 1 by A naught. This is for different unit wise rate constant rate law, right? So we can see here first order with respect to A, it's only S power minus 1. Right? Zero order is mole second power minus 1. For second order, for example, 2 reactant, overall it becomes second order. So M to the power of minus 1, S to the power of minus 1. If it is a third order, you can see M to the power of minus 2. Now we are going to talk about the rate constant for equilibrium, right? Reversible reactions. A gives B and B gives C. That's a forward reaction rate constant. There is a reversible rate constant, reversible reaction rate constant. So then there is a formula. This is just for your information. I have given the formula, and I didn't hear there are some question is being asked related to this kind of reversible reaction. Anyhow, you can just go through that. It will help you. This is for consecutive reaction. How to calculate. Now, these are the complete derivation. That is not important for us. Remember about consecutive reaction. And this is for a single reversible reaction. And this is 2 reactant with a reversible. So they have given the concentration, how to calculate. Right. Rate overall order of reaction is a sum of individual orders. So Ka, this is M and this is N. Okay. So you can, if you can sum of the overall the individual orders. I mean A to the power exponent is a power 1 and B to the power of half and this 2. Then it is a 3 order 3.5. I would say is a overall order is 3.5 or I would say 4. That way you can calculate the overall order of a reaction. But in our UPDA exam perspective, maximum third order wise, you can know about the unit and some formula, and first order and second order. That's very, very important. Normally, I get a feedback. They're asking some calculation question. Next is we are talking about the half-life. Half-life means is the time taken of the concentration of reactant to drop to half of its original value. That means half of a initial concentration. That's called half-life period. H naught, A naught divided by 2. That gives the concentration of A. That means T and off. For first order reaction, T and off equal to ln2 by K. So that ln2 value is 0.693. For T and off, half-life period for first order is 0.693 divided by K. For second order reaction, it is T and off equal to 1 by K A naught. For zero order, it is a naught by 2K. So remember, zero order, second order, first order, these three for T and off. The next is talking about the how we can arrive the rate constant. This is a Arrhenius equation talking about the temperature dependence of the rate constant, right? So which is equal to AE. They are talking about K is function of temperature. K equal to AE to the power of minus EA divided by RT. EA is your activation energy. R is your ideal gas constant, which is 8.314 joule per Kelvin mole. That's R. T is your temperature. K is your rate constant. K is nothing but rate constant. How to calculate? If by different temperature, if you take it, then you can calculate AE to the power of EA minus RT. Activation energy, gas constant, temperature. A is your constant value, right? It's known frequency or pre-exponential factor. There is also A and EA specific to the given reaction. So that will be something like a constant or given value it is there. From there, we can calculate K, rate constant. This is a CSTR, continuous stirred tank reactor. Before going to the CSTR, we will take some examples, then we'll come to the CSTR. Okay, first question. I want you all to hands-on. So the activation energy of a first order reaction is 50.2 kilojoule per mole at 225 degrees centigrade. At what temperature will the rate constant double? How to calculate? EA is given, temperature is given, and they're asking at what concentration will the rate constant double? Anybody has any idea how to calculate?
So we have to use Arrhenius equation.
Exactly. Yeah. Exactly. So we go back to this Arrhenius equation. Let's take it K1. Okay, K1 equal to AE to the power of EA R T1. T1 is given 25 degrees centigrade. Okay, then the T2, which is we do not know, but K1 by K2, which is a double, right? So that means K2 by K1 is 2. So you take it at a divided by. So AA will be cancelled. Understand?
Not clear, ma'am.
See, question is the activation energy of first order reaction is given. EA is given. Temperature T1 is given. You have to calculate T2. All right. At what temperature will the rate constant double? So there is a two temperature, two equation. But the key thing to relate these two equation is K2 by K1 equal to 2. K2 is the rate constant. So K2 by K1. So you have to divide it by these two. So AA will be cancelled. K2 by K1 equal to 2. So you have a EA e to the power of minus EA RT1 divided by e to the power of EA minus RT2. Isn't it?
Yes. And how about these units, ma'am? Is it directly we can use it? That E.
Only the temperature you need to convert, because the rate constant it is given 8.314. Even that also will be cancelled if I guess. R is going to be divided by R, right?
Yeah.
So only the temperature, because temperature is in Kelvin. So temperature only you need to convert. Right? So if you substitute, you can see here K2 equal to 2 K1, because exponential to the power of EA by RT, isn't it? So that's why I take it as a ln. Right? So K2 by K1, ln 2 equal to EA divided by R into 1 minus T1 minus 1 minus T2. You understand how I write? So you remember this formula also. If you have a 2 temperature, 2 rate constant, instead of deriving it when in the exam, just remember this formula. K2 equal to 2 K1. So ln K2 by K1, EA by R, 1 by T1 minus 1 by T2. Can you calculate and here tell me whether are you getting the same answer? Please, you use your calculator or mobile calculator or a system calculator. EA is given, R is 8.314, temperature 292 Kelvin. So you have a T1 is given, T2 you have to calculate. Please hands on with your calculator and check whether the answer is correct.
Madam, but we are only able to use normal calculator, right? Then how we can use log ln K2 by K1?
Why normal calculator?
We can use, can we take a scientific calculator during exam?
In the system calculator, there is a scientific option is there.
Okay.
There is a, if you click, let me check, I'll tell you. If you go to the computer system calculator, there is a one button you can click, then it will go into the scientific functions. It is there as a scientific itself. There is ln option there in your system calculator. Click scientific. That is a standard, different type of calculator in your system calculator. Standard, scientific. If you click standard, it is only plus minus 1 by x, like that only will be there, right? So you click this scientific.
Yeah, got it.
Yeah. Hi, Majid, can you hear me? Your audio problem solved today?
Yeah. I am following you. No problem.
Very good.
This reaction.
Sorry, Majid, I suddenly accidentally mute your audio. You were saying something.
Okay. Actually, this is a reaction engineering, yeah?
Reaction kinetics, yes.
Okay. Searching for LAN and calculator. No problem.
In system calculator, ln function is there. Click scientific, you will get ln. If you have done, if you are getting the same answer, then only I will move to the next. EA. So anybody completed?
I'm getting a very small value, 0.114. Is there some mistake I did?
0.1.
No, actually, there is one thing we have to calculate. E, they're giving kilojoule, and R value is in joule. So we have to convert this R value to divided by 1000.
Exactly, correct.
Yes, I think that is a mistake I did.
But if it is say only 1000, it is only you are getting like 3.3 or
Yeah, I'm getting 0.114.
then then if you multiply by 1000 also, it only give you
No,
110.
No, I think I need to redo it. 3000.
Okay, please redo it. Yeah. It's actually EA by R T1. So the R into 1 by T1 minus 1 by T2, the whole thing going to be the denominator, not EA by R and multiply by 1 by T1, not that way. No, I think there is something, some people have some confusion. Let's go back here.
I'm getting 303.
303. Okay, what is the answer here? 308.
308.
Something similar.
307 like that, 306.77.
306.77. That could be
We're getting around 308.
Yeah. Everybody having different number. Something around 307 plus. Shall we move to the next question? Is there anybody doing calculation still? Everybody getting 308? Anybody still working on, or shall
no.
I move to the next question?
Okay.
Somebody say something. I couldn't hear you properly.
No, it's okay. Fine.
Fine. So we can move to the next question then. Right. The second question. Certain reaction proceeds through first order kinetics. The half-life of the reaction is 180 seconds. What percentage of initial concentration remains after 900 seconds? First order reaction, half-life is given. They are asking what percentage of initial concentration after 900 seconds. How to calculate? Can somebody share some formula or whatever you remember the method?
Madam, if again we can go from the first slide, then we can note down the formulas.
Exactly. Very good. Here, come back to here, the half-life. This is the half-life, right? For first order reaction, half-life period is given, some 80 seconds or something. So from there, K you can calculate. Okay, this is the first order reaction, half-life period, half-life formula. You can write it down, T and half 0.693 divided by K. Okay, for zero order, A naught divided by K, 2K. For second order, T and half equal to 1 by K A naught. Please note it down, these three formula.
First order and zero order is okay. Half-life is T1 by 2. Yeah, bottom.
This one, this is for second order. T and half equal to 1 by K A naught, that is for second order. For zero order is A naught by 2K.
Okay, note it down.
So everybody note it down, three formulas for half-life. T and half for first order, T and half equal to 0.693 divided by K, that is for first order. For zero order, T and half equal to A naught by 2K. And for second order, T and half equal to 1 by K A naught. So are you completed noting down this T and half formula? Can I move to the other slide?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay, now we go to this one. For first order, ln A equal to ln A naught minus KT. Because the question is they're talking about 900 second, what is the concentration, right? So K we can calculate from T and half. That K you can substitute here. T is 900 second, K is given, right? Then you can calculate the ratio, like, you know, A by A naught, that you can calculate. So this is for first order reaction. Now to calculate the concentration at time T, which is ln A equal to ln A naught minus KT. Then for second order reaction, 1 by A equal to KT plus 1 by A naught. Please note it down, these two formula. Or A equal to A naught into E power minus KT. This also you can note it down. If you are noted down already, then I'll go back to the question.
Okay, ma'am.
Done. Yeah,
Done?
done.
Three for first order, A equal to A naught into E power minus KT, which is nothing but ln A equal to ln A naught minus KT. For second order, 1 by A equal to KT plus 1 by A naught. Then now we go to the question. So can you calculate half-life reaction is given, T and half is given, first order. Can you calculate K? Tell me what is the value of K?
So 0.00385.
Okay, then can you try the how to calculate the what percentage of initial concentration? This is a first order. A equal to A naught into E power minus KT. Here T is a 900 second. K you have calculated, right? What percentage? That means you have to take A by A naught. A by A naught equal to e power minus kt. So then you calculate A by A naught value. How about K value for others? Are you getting the same value?
Yeah, yes, ma'am. 0.017.
Yes.
0.017.
0.00385.
That's what somebody says 003. Is it 0.00385 or 0.017? What are the other value? There are two value now.
0.008. Sorry, 385.
385. How about others?
0.
Can you check? Somebody said just now 0.017. Can you check whether are you getting? Is there anything? It's simple calculation, right? The here time is in 180
Yes,
seconds.
correct,
You end
ma'am.
up
0.00385. Yeah, I did a mistake.
0.693 divided by K. So K equal to 0.693 divided by 180. Am I right?
Yes, correct. Yeah, simple one.
So the answer should be 0.00 something 3. Can you calculate A by A naught for first order? Then we can calculate the percentage.
3.12%, ma'am. It's coming.
3.12.
Yeah.
How about others? Any more answer?
We need to calculate A by A naught, right?
Yes.
Yes, 3.12%. It's coming 0.03127.
Any more answer?
Point 0.0312.
So that's a 0.0312. Here it is a percent, right? So you need to multiply by 100. So it's a 3.12.
Okay.
Yes.
Yeah, answer A.
Answer is A. A by A naught equal to e to the power of minus kt. K you can calculate from ln2 by k, which is 0.00385 per second. So answer is E. Everybody hands on already? Is this clear, this question? Or still anybody doing calculation?
Completed.
Completed. Very good. So we go to the question number 3. The reaction is given. Stoichiometry reaction 2NOBr gives 2NO plus Br2. This is a second order reaction. So with respect to NABr, K value is given at 10 degrees centigrade, right? And NOBr not, initial concentration of NOBr is also given. How much NOBr will be left after reaction time of 10 minutes? How to calculate? This is a second order reaction, right? So second order reaction, the question is how much NOBr will be left after reaction time of K? 10 minutes. So time is 10 minutes. You have to use a second order reaction. What is the second order reaction to calculate concentration?
1 over A equal KT plus 1 over A naught.
Right.
1
So
by
K
A
is
naught.
given,
Yeah.
A naught is given,
Yeah.
time is given.
So
So
what-
straight away.
K is given, A naught is given, time is also given. Yes, ma'am.
Yes. But thing is, one clue here, K is given in second, but they're asking in 10 minutes. So convert that one also in second. That's it.
So it's the answer C.
C 0.0016. Okay, any
Yeah,
more
point.
answer? We will wait for others to complete. Let's see.
It's answer A, 0.002.
1.6 into 10 to the power minus 3. C, answer C.
So 0.0016 or 0.002?
0.002.
0.016. I'm getting 1.6.
So 0.0, there are two answers now in the group, 0.0016 and 0.002. Any more answer?
0016. C.
C. C is the answer. It's only one decimal. You check, maybe you have done something number, when you press it, maybe something different number, right? So you check it again. Who said 0.002? You check your calculation again. Are you getting 0.0016? Is this who got 0.002? Is it Balaji or
Aman.
Amman? Okay. Is it now okay? Are you getting 0.0016? What
I
mistake
think we
you
are
made?
getting 0.002.
I'm
0.002.
getting 0.002. I don't know, but K is 46.6, right?
What is
We
the
have
value of
to-
K?
46.6.
How about others? Are you getting 46.6? Nitya, what is your K value?
Is it 0.8? The K
K
value
is
is
already
The K value is
given.
K
given,
value
right?
is already
Given.
given in the question. K
Yeah,
value.
point
K
0.8.
value
But it
given
is in
the
seconds,
question.
so we convert into minute, no?
No, we are
No.
multiplying.
You have to convert it reverse. 10 minutes you convert into second.
Yeah, no problem.
You 10 minutes you convert into the minute. Then T you substitute at a 600 second.
I'm
Okay.
getting answer D actually, 0.0011.
1.
Which one?
The A value.
See, there are 3 answers now. A, C, D.
K value is already given and T is 10 minutes. That is we converted into seconds. So
600 second.
600 seconds and A naught value is already given as 7.5 into 10 to the power minus 3. So substitute directly.
0.0075. Right? A naught is 0.0075 and T is 600 second. Very straightforward. Why it's giving that much time? Okay, let me check. K
Now
is
coming 0.0016. 0.0016.
0.0016, correct. Into 600 plus 1 divided by 0.007.
اوكي يعطيهم. لا دقيقة بس أنا شوية مشغول.
0.00161, right? So
Yes, yes, yes.
0.0016 is the right answer.
Yeah.
Right. So we move to the next question, fourth question. This is fourth question is being repeatedly asked, and NOBR is being asked. Okay. Okay. Catalytic process for the removal of SO2 from flue gas by reducing the SO2 to elemental sulfur using methane has been tested. So there is a catalytic process, right? And from the flue gas, they are, that is SO2 from flue gas, they are reducing into the sulfur. There is a two reaction. One is a mean reaction, another one is the undesired reaction. So in the main reaction, sulfur is being formed, reduced, and another one, SO2 converted into H2S, which is an undesired reaction. And what is the thing given? For two reaction, they have given the rate expression and your activation energy. Okay. So what is the question? Two desired, one undesired reaction, one desired reaction is given, and rate expression, not rate constant, rate expression and the activation energy of each reaction is given. Now, what is the question? Question is, in order to enhance the rate of a desired forward reaction relative to that of undesired side reaction, which of the following strategies should be adopted? So the question is, what strategy you will adopt to enhance the desired reaction and minimize the undesired reaction? That's it. So there are 4 strategies given. Can you please go through that and let me know what is going to be your strategy? You want to put a more desired reaction, you want to reduce the undesired reaction. So what is the clue here? How you will decide your strategy?
I think if the order is second, we will increase the concentration for the desired reaction. Increase the concentration of the feed,
Okay.
and increase the temperature. Increase the temperature also.
Temperature also increase and concentration also increase. This is what your strategy. That means answer is A, your preference. Increase both the reaction temperature and the concentration.
No, not both. For the desired concentration and the temperature, we need to increase, I think.
No, you go through A, B, C, D. Tell me which answer you are preferring.
Okay.
So you need to more favor to the forward reaction and less undesired reaction. So you need to choose one of the strategy which is mentioned below.
The desired is O2, yeah? Or desired, can you return back?
No, you can see now. So the desired reaction is forming H2S. Undesired reaction. The desired reaction is forming sulfur. Undesired forming H2S. That means reaction 1 is the desired reaction and reaction 2 is the undesired one. What strategy? Any option or anything?
No idea, ma'am.
Anybody? No idea? Nothing? So what is the clue here in this given, in this question?
Activation energy.
Activation energy, correct. So activation, which one is our favor reaction? This is the reaction 1. So reaction 1, activation energy is high. That means you should keep the temperature high, isn't it?
E minus EA over RT, yeah? So,
yeah. So activation
okay.
energy depends upon the temperature generally. It's a function of temperature, right? So you have to increase the temperature. Then there is a two option here, whether increase the temperature with the concentration also increase and decrease the concentration, right? So the most preferable is a decrease the concentration. Why? Because if we increase the concentration, both reaction will get increased because both are dependent with the concentration of SO2. So the right answer is B. Increase the reaction temperature and decrease the concentration of SO2 in the feed. That will favor more to the desired reaction. Okay, understand? So the answer is B for this question. How, based on the activation energy and the concentration of SO2 is required for both reactions. So if you increase the concentration of SO2, both reaction rate will increase. So for that, you need to maintain, or I would say decrease, right? Decrease, or I would say maintain some concentration or optimal concentration of SO2 and put a higher temperature. That will more favor to the desired reaction. This question is being asked for many question papers. I got a feedback. This for reaction kinetics, it is being asked. Okay, next question is talking about the CSTR. Okay, CSTR, we will go and see some theoretical formulas and all. Then we come back to the question number 5. Now, CSTR, continuous stir tank reactors. We know that is a feed. We are continuously going into the reactor and we are getting continuously output. This is a continuous stir tank reactor, which is a CSTR. Again, you have to take a mole balance for some component. I stands for input, O stands for output, right? This V is your volume of the tank. Capital V is your volume of the tank. Small v is your volumetric flow rate. Okay. X is the percentage of conversion. F flow rate, C means concentration. Okay. So in minus out plus production, which is equal to accumulation, right? If accumulation, if steady state, if you are assuming a steady state, there is no accumulation, then you can substitute here, right? Finally, you don't need to remember how to derive. Remember some formula, which is a flow, right? Flow, molar flow rate, which is equal to concentration multiplied by the volume of the tank. Okay. Flow equal to concentration multiplied by volume of tank, and the volume of tank, which is equal to percentage of conversion multiplied by the flow rate divided by the rate constant. Remember this, V equal to XA into FAI divided by minus RA, then F equal to CV for A component or output or input, that is. Okay. If you remember that one, we take volume of tank equal to XA FAI divided by minus RA, substitute F equal to CA by P. The red color, this is, sometime they will give the flow rate, sometime they will give your concentration and volumetric flow rate, right? Small v is your volumetric flow rate. They will give a rate constant. They will ask you required volume of the tank. So you can calculate from this formula. If you know the percentage of conversion, which is X, if you know the concentration of A in input, if you know the flow rate, like 1000 liter, 1000 meter cube, that's a volumetric flow rate divided by the rate constant. Sometimes rate constant you can use they will give a rate constant. Otherwise, you have to see the rate first order reaction. That formula 1 by A equal to A naught. That way you can calculate the rate constant, then substitute here also. So whatever given in the red color, that is very, very important. Okay, V equal to XA into CAI, V divided by minus RA. Remember. The next key thing is a Damholder number. What is a Damholder number? That is a dA equal to tau K. What is tau? Tau is nothing but capital V by small v. That's in terms of a number it is given. If I have to have a volume of a tank versus a volumetric flow rate, so that they make it as a one constant, volume of the tank divided by volumetric flow rate, that is a tau, multiplied by the rate constant. Yeah, somebody is asking something.
This one resident time, I think, yeah.
What is it?
This is called resident time.
Not resident time. Tau is some number. They say here, you can see reaction rate divided by the flow they are talking about. That's it. It's some number to specifically you can calculate for first for that particular volumetric flow rate and the volume of the tank. That correlation. If I have to increase the volume that much, then you have to put your volume of the tank that much. So the Damholder number defines finds the intercorrelation between the volume versus volumetric flow rate, which is equal to, if you substitute here, you will get a percentage of conversion divided by K into 1 minus XA. So then this equation, you can write it in terms of Damho number, dA, right? This is TK, dA divided by 1 plus dA equal to XA. So sometime they will give a volume of the tank, volumetric flow rate, right? Then you can first order reaction, then you can calculate K. So tau K is your downhole number. So if you know the downhole number, then you can calculate the percentage of conversion. This is in terms of percentage of conversion with the downhole number. This is percentage of conversion with the tau, and this is with your initial concentration with the final concentration. So whatever I have given 1, 2, 3, 4, and this formula 5, and this is V equal to XA FII. This is same thing here. You know, this formula, if you remember, FI is nothing but CI to B, right? So if you this 4 formula and tau Damhole's number equal to tau K. So this all, if you remember, for CSTR, you should be able to answer the question whatever they asked for. This is for second order. Whatever we are talking about here, it is for first order, and this is for second order reaction. So far, there is no second order reaction they have asked for it. So, but for your information, I have given the formula alone. Then this is called a resident time, just now say, or reaction time formula. Right? For batch CSTR, the reaction time for first order, it is given ln into 1 divided by 1 minus x divided by k. This is the reaction time formula. Please, reaction time for first order, second order. Please remember. So for kinetics, you need to mug up some formula, like same like your heat transfer. The heat transfer, we talk about Prandtl number, Reynolds number formula. Laminar flow means what is going to be your heat transfer H formula. So this all you should mug up. The same way reaction kinetics, some basic formula you should mug up. Right. So can you all write it down, this formula? Then we move back to the question. Okay. And I have some more theoretical chapter also. Before that, can you write it down, all the red color formula? Okay. Once you copied, let me know, then I'll move to the next slide. Put it here, CSTR, first order. Second order, it is given, but for now, I don't think you need to write it down second order. Only note down for first order.